Myself, Hariom Vats, welcome you to this discussion on our variable sun. This program is being organized by Space Education and Research Foundation at Ahmedabad, India. And if you have any question, comment, suggestion on this talk or on the things that are being discussed in this, you can write to me on these email addresses. The sun, as we see, every day it rises in the east and sets in the west. And we see that the sunlight and also the heat that we get in the evening and also in the morning is much less than when it is overhead. But that is not the variability of the sun. That is because of the Earth's rotation. So because of the Earth's rotation, it comes overhead us and it or rises or sets because of Earth rotation. So that is not a variability of sun. Similarly, we also experience less heat and less light, or the duration of less light in winter than that in summer. That also is not the variability of the sun. That is because of the tilt of the axis about which the Earth rotates. So that is because of that. The season change because of that. That is not a variability of the sun. As such, sun to a very common man, from the common man point of view, is not a variable star. It is a star that has been shining like what it is shining today in long past, and also keep doing so in very long time to come. But there are variabilities. There are very effective variability of the sun, which we don't see, but it is experienced by several experiments and systems on the Earth, and not only on the Earth, but even on the other planets as well. So in this discussion, before discussing the variability of the sun, we will start with the basic features of the sun, and then talk about the variability of the sun, of some of the features that we will anyway discuss here. And this variability can be divided into two categories: the regular variability. By regular, I mean that they are repeated, not exactly with a constant cycle, but a reasonable constancy. And those are like solar cycle, solar length of the solar cycle. There is a Hale cycle. There is also solar rotation, which is also reasonably regular. The sun rotates and has lots of variation. We will discuss some of those variability in this talk later. There is a 5-minute oscillation, a very fine oscillations that are seen on the surface of the sun. We will discuss that as well. And at the same time, there are irregular variations like solar flares, radio bursts, coronal mass ejection, similarly filament eruption, prominence eruption, etc. So those are also very intense activities that take place on the sun or from the sun, and they affect us in a very dynamic way, in a very strong way, our communication and many things, many features that we clearly observe on the Earth are changed because of that. And the occurrence of these solar flare, radio bursts, coronal mass ejections, etc., are not regular. They irregularly appear. However, there is some regularity in the sense that, like in the when we will discuss that during the solar maxima, they occur more, all these. During minima, they occur less, but they occur everywhere and with a very fair amount of irregularity, which means that the time separation of two events is not predictable. There has been very large effort going on world over in the field of solar research to make these irregular variation predictable. But so far, we have not succeeded. A lot of work is being done on that. So now let us start with the basic features of the sun. The sun, as we know today, can be divided into several parts. One of the most important part of the sun is this the innermost portion of the sun, which we call core. And in fact, the temperature of the core is so high, the material density is also very high, that here the fusion reaction can naturally take place. And not only in sun, but all these kind of stars that we see, there we can see this. So this core which is here is the furnace where the fusion reaction takes place. The hydrogen combines to make helium, and there is a mass loss. That the amount of hydrogen that is used is more than the helium that is produced, and that excess mass is converted into energy, which yields a very large amount of energy. So that is the main source of the sun's energy creation is here in this core. And it's a very huge energy. And this energy, when this energy is produced, it also tries to expand the star, expand the sun. And the gravity tries to make it compact. And these two forces, the gravitational force, which tries to make it compact, and the force, the energy which is produced here, that also applies a force to sort of expand it, are more or less in balanced state. And sun, as we know today. And not only sun, most of the stars that are in their main phase of their life, these two forces have to be balanced. If one increases, the other will automatically sort of balance it. So that is why the sun has been shining like what it has been shining for past many, many years, and will continue to do so for many, many more years to come. So that is the because of this process. Then there is a very dense region around it, where the energy that is produced in the core is transmitted upward, and then transmission is by radiative process. And that is why the region marked 2 is called the radiative zone, in which the material does not move. From one particle to the other particle, the energy is radiated, received, re-radiated, and so on. So the energy propagates. Above that is this third region called convection zone. This is a region where the energy is given from the radiative zone to this, and here the density is though high, but not as high as it is in the radiative zone. Here the material can move, and that's fun. So it takes energy from here, goes up, and comes back again, passes energy here. So that is the convection zone, where the energy is sort of transported by process of movement. Above that is this fourth region, fourth part of the sun, called photosphere, marked here. This is the part that we normally see during the day. Very easily, by putting a sunglass on our eyes, we can easily look at the sun and you see it very beautifully anywhere in the world. But on this also, there are features, many features are there, like sunspots are one which is very prominent. We'll discuss about these later on. These are like a magnetic storm on the sun's surface, and they appear to be less bright than the rest of the sun, and that is why they are fairly high temperature, but the temperature inside this is less than the rest of the sun, because here the material from inside comes out and then gets spread, and when it spreads, the temperature falls. So it becomes a relatively darker region, and these are called sunspots. On this, there are also features like these marked here, like these. These are called prominences, that there is the material, it is a sort of a eruption of hot gas from the photosphere. The material can go thousands of miles up into space and then fall down. So that makes, and these prominences, because sun rotates around its axis, so when we see it somewhere here on this limb or this limb, they appear very bright. But same thing when it is on the surface here, inside on the surface of the sun is in the background, then the light that comes from the photosphere is sort of gets blocked by that feature which is outside the solar surface, and then there we call it filament. And the very extended region of the sun is called the seventh region, that is the outermost part of the solar atmosphere, is called corona. And this is the region that we see only with a very spatial arrangement or during the total solar eclipses. During total solar eclipses, we can see this region very easily. And the another important thing is, like the core is at very high temperature, the temperature in the radiated zone is less, that of convection zone is even lower, the photosphere is at lower temperature, but the corona, which is a very large sort of blob of gas all around the sun's surface in sun's atmosphere, is very hot, is almost as hot as the core itself. And this heating is is also a matter of research. A lot of research work has been carried out and is still being continued. And it is believed that the heat or the temperature of the corona, as we see, is very high. It's because the heating is provided by the waves that come from inside inner part of the sun and also the magnetic field. So the temperature here becomes more than 1,000,000 degrees, and the temperature here is also 1,000,000 degrees or more. And the in-between regions are at lower temperature. Now, the sunspots have a very special significance or special role that we see. Here are two solar images. This solar image, near solar minimum, that of January 2005. When we say solar minimum, that is the year or the time when on the solar surface, when we take a very detailed picture of the sun, we see almost no spot or very few spots. So that is this one. Here you see that there are no spots. And if you look at this image here on the left side, which is near maximum, about 4.5 or 5 years before, that is March of 2001. Here, in this image, you see that there are lots of spots. There are spots all over. Many are there. So, and these spots are so since we have more number of spots, so this time when sun has very large number of spots, could be 200, 300, 200 plus sometimes, or it also varies from year to year, but it can be of that hundreds of spots. Some are group of spots, and scientists have been sort of counting them, counting their area. So all that is, so this period when the number of spots are more on the solar surface, that is called solar maximum year. And about the sunspot, as I mentioned, their number change, their area changes, their shape changes, their size also changes. These spots, a very detailed picture of this spot is shown here. This is the region from where the material from inside the sun is coming up, and because it is thrown up, so it cools, and that because of that cooling, you see this region as dark, black. And then this is called the umbra of the sunspot, and this is penumbra of the sunspot. There are lots of studies of the sunspot that has been carried out, and these are very variable. Then about the spots take birth, they evolve in the sense in terms of area, in terms of shape or size. They evolve, they change, they erupt, and that eruption leads to solar flares or from coronal mass ejection, etc. And there are timings when the spot disappears, it dies, it's no more there. So there is a birth, evolution, eruption, and death of the sunspots which take place. And the sunspots have been very carefully observed for a very long time. There is a record of about 400 years of sunspot observation, starting from 1600 around that to about 2000 or more. And here you see that the ones that are shown in red color are not the actual observation. These are sort of the sunspot number obtained by proxies, by comparison, by a special kind of comparison. These things, this curve that shows here in blue color is the actual observation of the sunspot. The daily sunspots are measured and their number is plotted. Similarly, the area also is measured of the sunspots. And here you see that minimum to minimum, all these minimums, they are separated approximately by 11 years. Similarly, the peaks here and here, 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 all these peaks also are separated by 11 years. So, and so that is there is a reasonable regular cycle, and that is called solar cycle, which is around 11 years. In fact, first time in 1843, Swabe was a solar physicist who studied 17 years of solar sunspot observation and discovered that there is a cycle, and that cycle is around 11 years. Later, Wolf, another solar physicist, he tried to study even longer time of sunspot numbers, and he started counting the solar cycles. This cycle 1755 to 1766, that is here, is called the first cycle, and then the first, then second, third, and so on. Right now, we are in cycle 25. So every roughly 11 years after, the cycle number changes. And interestingly, in this proxy, the sunspot numbers that are obtained by the proxies, there is a very low number of spots for a very long time, almost about 40, 50 years. And this is called Maunder minimum. And it's also that the historical records indicates that this was a little ice age. The temperatures in the northern hemisphere where people used to live were very, very cold. So, which indicates that the sunspot variation, especially this variation, that it remained low for a very long time, which resulted into little ice age, and the sunspot make a very significant effect on the climate. We will also talk a little more about this in the slides ahead. Here also, the sunspot number is shown. Here the background is that of the X-ray sun. And this slide is from NASA Hathawa's slide of NASA. And this is the time in years. The time changes here. This is about 3 solar cycles, cycle 23, cycle 22, cycle 23, and cycle 24. And cycle 24 ended recently, and now right now the cycle 25 is continuing. And in this also you see that the number of sunspots are mentioned here. You can see the highest that is observed in the past few solar cycles is very close to 300. That was the highest. And the another thing that you see, that this peak here and the peak here, there is downward trend. And if this downward trend continues for a long time, we may end up into Maunder minimum kind of condition, which also worries the scientists today. But because there is a decrease here, there is decrease here, and if this decrease continues in cycle 25, 24, and so on, and becomes low, so we may end up having a sort of a little ice age, which will be very difficult to handle today. This is another variation of sun shown here. Again, it indicates from solar maximum to solar minimum. This is year 1991 to 1995. And these are typical X-ray images, solar X-ray images, the observation of sun in X-rays, which were done by a satellite called Yoko, a Japanese satellite. And here you see that here the X-ray flux is more, it reduces in this, reduces further, and continuously sort of keeps reducing. And in the solar minimum, which is 1995, there is a very low X-ray emission. So this indicates that not only that the number of spot changes, even the emissions, X-ray emission, UV, many emissions from the sun, even the sun's total, we will discuss the irradiance in the next few slides. There also you see a change of the intensity of those parameters from solar maximum to minimum. In minimum it is least, in maximum it is highest. And these part 1991 to 1995 is the descending phase of cycle 22. Descending phase means when the sunspot numbers are on the decrease. This is a very interesting picture from Solanki 2002, his talk, and he sort of depicted here the total irradiance measurement from various programs. The name of the programs are mentioned here. And you see that there is a large variation, and this much large variation is typically 0.1%. So the variation is though small, but this has a sort of trend. If you put the trend line, that it decreases, increases again, decreases here, and this is about two solar cycles. So here, from this maxima to this maxima is about 11 years. This minima to this minima is at 11. So there is a solar cycle variation in the irradiance as measured by various programs. And Solanki 2002 also showed a very one-to-one sort of relationship of the sunspots with the irradiance measurement. In this curve is from 1st November to about 20th December 1996. 1st November 1996 to December 1996. So this is the variation of irradiance that was observed. And here are specific images of the sun. This image corresponds to this day. This image corresponds to this day. This image corresponds to this day, which is this dip also, and then this here, and then this one. And there are these spots, this two pair of sunspots that you see here. They are at almost on the limb here, and in the next image they have moved inside, and here they are exactly at the center. And when these are at the center, the irradiance is least, and then when it tries to go to the other side, the irradiance increases, and then when it is very close to the edge that is shown here, which means here it has come back to the normal, the average value. Here the irradiance variation is shown with respect to the average irradiance. That is why this scale is from -0.8 to about 0.5 units, percent, sorry. So it's a very small variation, but it depicts that this variation directly depends on the sunspots, and not only just sunspot, their position, where the sunspots are located on the solar surface. There is a vast amount of work carried out by Friis, Christensen, and Larsen in 1993, and their work in a beautiful way is presented by Solanki 2002, and that slide is here. Here are the two parameters shown. This orange color parameter is the temperature, the land air temperature in the northern hemisphere. The temperature is measured at several places, and the average temperature is taken, and that and then also the temperature also was sort of running mean of 11 years also was taken, and that variation is depicted here by this orange curve. And this it is with respect to the average temperature of 1951 to 1990, and that is this will be this number. So these the negative temperature means it is less than the average of 1951 to 1980, and when it is more, it is in addition to that temperature, it is more. So that is shown here, average temperature, and the length of the solar cycle, which is also filtered in a very special way, and that filtered length of the sunspot length is shown here. This is the smallest, that's 9.5 years, and this is 11.5 years. That is the sort of variation in the sunspot length that has been observed. And this length variation and the land temperature in the northern hemisphere, there is a very good correlation. So again indicates that not only the sunspots number or their area make changes on the Earth, but even the length of the cycle also is important parameter. The the sun also has a magnetic field, and that magnetic polarity is also measured by this NSO Kitt-Peak field measurements, and it is shown here. And the specialty that you have here is, this is from 1994 to 2018 or 19, almost 2000. And this is called butterfly diagram. Butterfly diagram. And why it is called butterfly? Because, and the color code is shown here, shows the intensity and the color. The red color shows the north polarity, and the blue color shows the southern polarity of the magnetic field. And you see that here there is northern polarity, there is southern polarity, this is southern, this is northern, this is northern here, and southern here. And this picture is almost looks like as if it is a butterfly, and that is why it is called butterfly diagram. The important thing that to be noted here is that this cycle 22, which is these years, this cycle 22 on the northern pole, this is 90 degree, is the latitude, which means this is the northern pole, and this is southern pole. On northern pole is mostly the north polarity. On southern pole there is this is southern polarity, here it is north polarity, which is marked by red color. In the next cycle 23, the red polarity, which is north, is seen in the northern polar region, and the southern polar region has the south polarity. And in the next cycle 24, again it changes. It is southern polarity here in the northern hemisphere, and north polarity in the southern hemisphere. So these changes from north polarity to north polarity is after a full cycle, which means this has a periodicity of 2 solar cycles, which is called Hale cycle. And the same thing you can also observe here, that this is more red dominated region here, blue dominated region here, and this is again the red dominated. This red dominance is after 2 cycles. This cycle 22, this cycle 24. Cycle 23 was of the opposite side. And same thing you see on the southern side as well. So this variation which you see from this butterfly diagram of magnetic field measurements of the sun shows that there is a Hale polarity, and the name Hale is given because it was discovered by Hale. So that is Hale polarity, Hale cycle, and that is 22 years. Now we go to another topic of a regular variation of the sun, is the sun's rotation, which we call solar rotation. If you take the picture of the sun any day with some, not a very big telescope, but some 3-4 inch diameter telescope, and you sort of play these pictures one after another. This is in fact the movie made by those pictures, and you see that the spots, they gradually drift up in this direction to the right side. And this in fact was the first indication which was given by Galileo almost more than 400 years ago, that the sun is not stationary, it rotates around its axis. So that is called solar rotation. And later on, many studies of this were carried on, and there are very intricate variations that has been observed. Some of these I will try to describe in the next slide. But before that, let us discuss primarily the primary methods of solar rotation estimates. The estimation of solar rotation is done by three methods. The first method, which was used by Galileo, that is called tracer method, in which you take an image, and like you have seen the sunspot, you see its position today, tomorrow, day after, and so on. And then from there determine how fast it is rotating. Okay, so that is by the trace. This is the first one, that is which was used was sunspots. Later on, many scientists have used filaments, plasmas, X-ray bright points to determine the solar rotation. Later on, when spectroscopy was discovered and was being used for solar observation, the spectroscopic method also can be used to determine the rotation of the sun. And this has been used for quite some time by many researchers. And in this, essentially, what you do is, because if the sun is rotating around its axis, there will be one part which will come towards us, the other part will go away from us. The part which is coming towards us, that will the frequency of any emission that is starting from the sun, that frequency will increase, and the same emission from the part which is going away from us, that will be, the frequency will reduce, which is called redshift. There will be blue shift on one side and red shift on the other side. And by the difference of these two shifts, the red shift and blue shift, one can estimate the rotation of the sun. There is one more method which our group at Physical Research Laboratory in Ahmedabad used very extensively, is called flux modulation method. And this flux modulation has been used using disk integrated radio emission from the sun. This has been used on the radio images of the sun taken from the ground. This also has been used by X-ray images of the sun, which were made by the satellites like Yoko satellite, and EUV images of the sun, which also has been are regularly being taken by SDO and several other satellites. So they all can be used to determine the solar rotation with this method, the flux modulation method. I will give some presentation of the results that has been observed, and these are mostly from our group. This is a result of Watts et al. 2001, where for the first time the coronal rotation, how the coronal rotation depends on the height in the solar corona. And this work is essentially done by using solar radio emission at 11 different radio frequencies. And these radio frequencies, different radio frequencies, will come out, will emanate from different height in the solar corona. The higher frequencies will be emitted from inner corona. The lower frequencies will get emitted from the higher corona which is away from the photosphere. So here the height above the photosphere is shown in the units of 10 to the power 4 kilometers, like 5 to 13, 15 into 10 to the power 4 kilometers. And here is the sidereal rotation period in days. The variation, like this one is about 23.7, and this is about 24.1 or a little more. So this means this is about a half a day variation that is seen in the sidereal rotation at a height range from 5 into 10 to the power 4 kilometers to about 13.3 into 10 to the power 4 kilometers. So the rotation decreases, rotation period decreases as you go to the higher heights in the corona. So it was a very interesting observation. A lot of work has been carried out after that, and it's also being done even now. Another very interesting study using the flux modulation that has been done is using solar soft X-ray images, SXT that is called. Solar SXT, solar X-ray telescope measures the, take the images of the sun. And here this analysis, this picture is based on the images from 1992 to 1995, daily images of this part of the cycle 22, which is the declining phase of solar cycle 22, are used in this to make this diagram. And here on the x-axis you have latitude, -80 means towards the southern pole of the sun, and this is the 0, the equator of the sun, and this is the northern pole or towards the northern pole of the sun. And these are the years from 1992 to about 1996. And the color that you see here is coded like this, that this color indicates 24-day rotation period. The color indicates the rotation period. This color, which is here, several places, is 24-day rotation period. This color is 25-day rotation period. Green is 26-day rotation period. And this orangish color is about 27, and this red is 28 days rotation period. And so that the variation of rotation period is depicted here. So you see that in the equatorial region of the sun, the rotation period is least, is mostly 24, 25 or less. That's sidereal rotation period. Whereas when you go towards the higher latitudes on north side or on the southern side, there is an increase. In fact, the average of all these years is shown by this line curve here. And the scale of the line is depicted here. That like here it is about 25 days, and on the northern pole or close to the northern pole, it becomes 25.6 days, whereas in the southern side, it's about 26, slightly less than the 26. So there is a differentiality. In the northern hemisphere, it is lower on the average. You can also see the same thing by this color code, but here the yellow and red color is almost absent. Only green, which means about 26, is here, and that is why the average is 25.6 days. So it's on an average, it is more than the equator, but it is not as much more as it is on the southern side. So southern side, the rotation period is higher. And because you have this red and yellow color indications here. So that is the asymmetry. This also was sort of shown for the first time, that the sidereal rotation period in the solar corona, because the X-ray emission comes from the solar corona, that there is a asymmetry in the rotation period. And interestingly, this is the cycle, declining phase of cycle 22. Now we'll go to the rising phase of cycle 23, the next cycle, which is from 1996 to 2001. And here also the same X-ray images from the X-ray telescope are used. for this period, and the rotation period is depicted by the same color code which is here, and it is shown here on this. These are the latitude from -80 to +80 degree, and this is the time from 1996 to 2001. And here you see apparently that this color more or less indicates that it is symmetric. There is a low rotation period here, and it increases on both sides. And if you take the average of the all these years, then it varies like this. So it's almost symmetric. So it was asymmetric in the first half solar cycle. In this half solar cycle, it has become symmetric. And now we go to the next set of slide, where it is for the declining phase of cycle 23 on a next part of the solar cycle. And here, this is not by X-ray, because Yoko did not work at this time, but these are from the radio images taken at Nobeyama radio heliograph at 17 gigahertz. This also is a coronal measurement, though at a slightly different height than the X-ray emission on an average. But interestingly, this also depicts a very clear picture that the rotation period near the equator is least, and it increases on both sides. But here, the increase is opposite to what we have seen in the declining phase of cycle 22, which is about 11 years before. There, the rotation increase was more towards south. Here, the increase is more towards north. So this asymmetry is there. It was south was had more period in the cycle declining phase of cycle 22. The rising phase of cycle 23 was more or less symmetric, and declining phase of the cycle 23 changes the asymmetry. So which is about 11 years. No, sorry, because from becoming from south more to north more, it has taken 11 years. So which means that this is only half cycle of this variation. So this is a 22-year variability that this observation indicate, a Hale cycle variation in the rotation period of the sun. So that finishes that part. And now we will come to the 5-minute oscillation. This also is a very interesting subject, and it's being continued as a regular study. And in fact, this have led to a very good field of research called helioseismology of the sun. And that I probably will not cover in this talk, and maybe sometime later, but has given rise to that field. And this is a typical image which is called Michelson Doppler Interferometer. This basically measures the Zeeman splitting of the emission from the sun, and this is converted into velocity, because this darker region is coming towards us, so the velocity is minus because it is coming towards us. So there will be blue shift, and the velocity decrease is about minus 2 kilometers per second in this region. And as you come towards the central part of the sun, or the equatorial part, the sun which is directly over us, there is no Doppler shift. And then of this side, the shift is going away from us. So the velocity will increase, and that is about 2 kilometers per second is the increase. So, and such images have been taken on a very long-term scale. The Leighton, Noyes, and Simon in 1960 showed a very interesting analysis of these images. What they have done is they have taken one of the image which was shown in the last slide, and they have taken 22 slides, 22 images before and 22 images after, and also this image. So taken the average of those 45 images. And then from the single image, the average of these 45 images have been removed. So that is removed, and then what is left over on the solar surface is shown here. So here the rotational component of sun's rotational component is removed, and this is the oscillations which are there on the solar surface itself, and their magnitude varies from something like minus 500 meters per second to plus 500 meters per second, and that is by this color code, right? You have these features, and if you take the linear values of this and make a plot, this by Howard, Tenbaum, and Wilcox in 1968, a part of their picture. And this is the distance from the central meridian in shown here in 10,000 in the units of 1,000 kilometers. So this is the distance from the central meridian of the sun, and this is the time in minutes, and these are the different curves which is obtained from those velocities curves that you see here, and the velocity scale is shown as 500 meters per second. So these variations are very large here. This is about 400-500 meters per second, and these are less. So you see that and then the time separation of most of these are about 5 minutes. So this is the time here is from 140 minutes to 60 minutes total, and say like from here to here is 10 minutes. So you have 2 peaks in this period. So this was the 5-minute oscillation which was seen for the first time. And this also is a very regular phenomenon. The helioseismology now gives more detailed analysis of the oscillations of the sun, and not only of the surface oscillations, but even the inner sun, and a lot of studies of the inner sun is being used by the helioseismology. Now we come to the irregular variabilities that are seen from the sun, which are like all these, the solar cycle variation, the Hale cycle variation, the length cycle variation, and also the rotation period in different parts of the sun, whether it is photosphere, corona, chromosphere, or transition region. There is a system, there is a reasonable sort of regularity in that, and even 5-minute oscillation, and also many other oscillations which are now being studied in helioseismology are regular variations. Whereas the features that we will discuss now are totally irregular. They appear as they like. This is one example of 14 July 2000. This is called Bastille Day event. In France, Bastille Day is their national day. And since it happened on 14 July, so that's why it is called Bastille Day event. And this was on, so this is the feature on the solar surface, from a very detailed picture of that. And you see that this is the flux tube, and it's twisting. And then several of these very white portions, it got sort of punctured because of the excess material inside, which the flux tube could not hold. And it resulted into a very large solar flare, a very large solar flare from the sun. And it also gave a halo coronal mass ejection. The CME means coronal mass ejection, CME from the sun. And the CME is a very massive amount of mass and very high energy charged particles that come along with this. Normally, the speed with which the material, coronal material leaves this sun in the form of solar wind, the velocities are of the order of 300-400 kilometers per second. But whenever coronal mass ejection takes place, these could be 1,000 or more, or few thousand kilometers per second speed material, and the density is more, and it has more charged particles associated with it. It also carries a magnetic field of the sun with it, and it interacts with the Earth's magnetosphere in a very different manner than the normal solar wind, and give rise to what is called geomagnetic storm. This event produced a super geomagnetic storm, which was experienced by the magnetic field measurements on the Earth from July 15-16 period. The magnetic storms are sort of measured. Their indication is derived by a parameter called DST, and the value of this DST during this period was minus 301 nanotesla. So, which is a very large solar storm, one of the largest solar storms that has been seen over past many years. And similarly, there was another event which occurred on 28 October 2003 in the declining phase of solar cycle 23. And you see that there are these burst-like structures. Suddenly, the material from here burst out. So there were 17 major solar flares and also associated coronal mass ejections that took place from this. And because this happened to be around Halloween, its effect on the Earth came at the time when Halloween, a Christian festival called Halloween, is celebrated mostly on 31st October. So since it was around that, so this is called the Halloween event. So this had the associated 17 major solar flares and CME were associated with this kind of very active sort of activity on the solar surface. And usually the coronal mass ejection that takes place, which is the huge cloud of magnetized plasma from the sun, takes place from the event that I just now showed you before. And this is measured by a very special instrument on satellite, where the sun is covered by this disk. This is the diameter of this is exactly same as that of the sun, and there is another disk which is twice the diameter of the sun. So even the inner corona also is sort of covered by this, not only the photosphere, but also the extended part of the corona is, and you see this mass flowing out. There are movies of this. I did not include that in this here, where you can see the material flowing out in these. By taking those images, in a big sequence and make a movie, and you can sort of present that this material is coming out from the sun. So this very excessive magnetized plasma cloud, which we call coronal mass ejection, came out and then interacted with the Earth's geomagnetosphere and created geomagnetic storm. It also created aurora, which was seen in the northern and southern hemisphere of the sun. And associated with this, the X-rays also come out, and their intensity also varies as a function of time. Here is the X-ray measurements shown from September 15 to September 8. And at two X-ray bands, one from 0.5 to 4 angstrom, and this is another measurement from 1 angstrom to 8 angstrom. So you see that there is a large variation in both of these seen. And these are classified, these X-ray flares, these are all flares. And these are classified as A, B, C, M, and X. When the flux is from 10 to the power minus 8 to 10 to the power minus 7 watts per meter square, that we call A flare, when changes within this range. When the changes from 10 to the power minus 7 to almost 10 to the power 6, those flares we call as B class flare. Like this one is a B class flare. This is a B class flare. These are also B class flare. But these ones are C class flare, where the flux reaches as much as 10 to the power minus 5 watt meter square. And if the sudden rise in flux rises to 10 to the power minus 4 watts meter square, then that flare, many of these are called M class. And if it crosses that and goes in this range, that is called the very, very energetic, very, very strong flare called X class flare. So these are the 5 type of X-ray flares that has been classified from weak to strong. A, B, C, M, and X. X is the strongest and A is the weakest flare. And associated with this, with these flares, or one of the flare which took place on 10th September, and its X-ray magnitude was 8.2. That means 10 to the minus 8, 10 to the it was very large, 10 to the power 8.2 watts per meter square. So associated with that is the particle flux. And this particle flux is shown in 3 different particle energy range. The particles whose energy is less than 100 MeV is shown by green color. The particles whose energy is less than or equal to 5 MeV is shown by blue color, and the red is the particles whose energy is 10 MeV or more is shown by the red color. And here is the sudden rise in all these. The rise in the is like the rise in green, which is the highest, most energetic particle, is about 3 orders of magnitude. That number increased by 3 orders of magnitude. And in these also, everywhere, it's almost 3 or 4 magnitude, the number increased. And these very large, very highly energetic particle and large number, when they come and interacts with the ionosphere in the northern hemisphere or near the polar region in the north and also in the south, they create aurora. A very beautiful, very colorful dance of light, which nature shows in both these polar regions. Now, the last thing that we discuss in the irregular variations on the sun is the radio burst, solar radio burst. This is a measurement of green bank solar radio spectrometer because which operates from 20 megahertz to more than 60 megahertz. So this is the frequency, and this is the time axis, and the color here shows the intensity of the radio emission that takes place. This is the high intensity, this is the almost the background, the lower intensity, this high. So like from here, this is brighter, more bright, and the red is the brightest. And the average of this is shown by this curve. This takes the average of the entire all the radio frequencies that are measured by this, and that shows this variation. That's the average from. So these are also, they in fact interfere with the radio communication on the sun. Many radio telescopes that are used for measuring or even our transmission gets directly, this radio flux comes and affects our communication signals on the earth. And there is a model of the generation of this type of radio burst from the outer part of the solar corona by Reid and Radcliffe, 2014. And here it shows that the radio frequency around 250 megahertz gets emitted in this region, and 10 megahertz gets emitted in this region, and all the way up to this, almost up to the earth, that there are emissions at various wavelength. The frequency of the emission decreases as we go from here to here. The higher than 250 megahertz comes from even inner part of the solar corona. So this is the model which depicts that, and these measurements have been made by using ground-based observation as well as by satellite-based systems. So with this, let us conclude the discussion for today. We discussed about the basic properties of the sun in this. There are quasi-regular variations that exist on the sun, and these are called solar cycle length variation, Hale cycle, solar rotation, 5-minute oscillation, and other oscillations as well. All these vary in intensity, duration, and periodicity. There exists a very significant north-south asymmetry of the solar rotation, which has been measured over these years in the recent past, and many studies of this are being continued even now. And this asymmetry also seems to have a periodicity of around 22 years. There are random or almost unpredictable, very energetic variations in the form of solar flares, radio bursts, and coronal mass ejection. And these specifically, these unpredictable, very energetic variations that take place on the sun affects our Earth's environment, produces auroras, which can be seen in the large part of the northern hemisphere around the polar region. In some very, very strong event, even one can see sometime aurora even in the mid-latitude regions of the Earth. But high latitudes is very, very, very common. We experience geomagnetic storm of different magnitude, and we experience disruptions in communication, the radio communication, the TV communication, and even satellite-based communication. So with this, I come to an end. In this talk, I have used material from research papers, books, and internet. I heartily acknowledge and appreciate the authors and providers of this academic material. Some references I have given here, but some are probably not, but I thank them all. Thank you very much.